Yes, welcome back, students. Today we are going to discuss the next topic of Module 5, that is tasks, processes, and threads. So, tasks, processes, and threads, these are related to the unit of work that is done by the processor. So, when I say task, it is some amount of work that the processor does. Process is also some amount of work the processor will do, and thread is also the some amount of work the processor is going to perform. Now, and when I will just try to understand with the term task, it refers to something that needs to be done, or you can also call it as the unit of work or some amount of work that needs to be done. And who is going to do this work? It is the CPU. So in operating system context, the task is defined as the program in execution. So the program which is loaded into the main memory and which is under execution is called as a task. And along with the program which is under execution, all its related information that is maintained by the operating system for the program combined together, you call it as a task. The program which is under execution and all the related information that is maintained by the operating system related to this particular program, we call it as a task. And you can also call sometimes the task as the job also. These two words can be they can used interchangeably. You can call it as a task, you can call it as a job, or sometimes you can also call it as a process. Now all these terms, they can be used interchangeably. Now you can say a program or a part of it in execution is called as a process. Okay, that is what is the process. The process is the active entity, whereas the program is a passive entity which is stored just like an ordinary file on the disk, whereas process is the one which is loaded into the main memory and it is the active entity. Now a process is a program, as already told, or a part of it. So even a part of a program can also be called as a process. Now why we say part of it? Because if it's not possible for you to load the entire program into the main memory for execution due to space restriction, then you can go for loading a part of it into the main memory. So then the one which is loaded into the main memory is not a complete program now. It is only a part of the program. So even the part of the program can also be called as a process. And you can call another way, a process is an instance of a program, because one copy of the program, if you write, any number of instances of that process can be created. So you can have the same processes for the program, same program which you have written loaded into the main memory and execution. This is what we call it as multiple processes. And then and process, when I say it represents the work that needs to be done by the CPU, and for the CPU, the CPU to finish this work, it requires some resources. One is the CPU itself is required. Apart from the CPU, it requires the memory, because for storing the code and the corresponding data, and also requires the I/O devices for information exchange, that is input-output exchange. Now, structure of a process. The concept of process leads to concurrent execution of the tasks, so thereby efficient utilization of the CPU and other system resources. So the concurrent execution is achieved through sharing of CPU among the processes. The one CPU you have, and you can go for sharing that CPU for executing multiple processes. Now, and I can say a process mimics the processor also, because a processor has something called as PCB, program control block. In the previous class I explained the task control block and the process control block. So since the data structure name process control block is associated with every process, now I can say the process mimics the processor, because the process also holds the set of registers, process status, program counter. See, program counter, process state and the registers, these are all the one which you find inside the processor. But so a process is something like a virtual processor now, because even the process also has a set of registers, so program status and the program counter. So when the CPU is switching from one process to the other process for execution, the current status of the process are all the values which are available inside the CPU registers, program counter and the program status get saved onto the PCB of the process which is currently under execution. Hence we say the process also mimics the processor, because the process carries all the properties that are currently available in the CPU. You can set of registers, program status and the program counter, everything can be saved. Now this is how you can visualize a process. A process is something like this. It has a stack, it has working registers, it has status registers, it has program counter, and the program counter it holds the address of the next instruction to be executed. That means it is pointing to the instruction which is stored inside the code memory. And then this is what the memory organization of a process. We have a code memory, data memory. Now, and this entire thing we call it as the address space of a process. An address space of a process comprises the code memory, data memory, stack memory and also the heap memory. So you know that the data memory grows upward like this and the stack memory grows downward. So and stack is used for storing the return addresses and all these things, and this is what the address space of a process. Now when I say a process address space, it has four major sections. One is code section, data section, stack section and also the heap section. Heap section is generally used for dynamic memory allocation. Now apart from that, why do we say the process also mimics the processor? Because within the PCB of the process we can find all the physical resources that you can find inside the CPU. So because we have working registers, all the registers which are available in the CPU can be copied to this working set registers which is available inside the PCB of the process. So this is the relationship between the process and the processor. So process, I can say it is the mimic of the processor. Now a process inherits all the properties of the CPU. So when the process gets it done for execution, its registers, program counter becomes mapped to the physical registers of the CPU. This is what I told. So we have the registers, working registers inside the process, program counter register inside the process, and all these things when the process is about to start its execution gets mapped to the physical registers, the actual registers of the CPU. So and then as already told, the process is segregated into three regions. So I'm showing here three regions, but strictly speaking process is segregated into four regions. We have something called as data section, code section, stack section and also the heap section. Heap section is not shown here, but remember, so a process has four major sections. Now one is stack section, which is mainly used for holding the temporary data, and of course this is also used for holding the return addresses. Whenever the process makes a call to function, the return addresses will be saved onto the stack. So data memory holds all the global data for the processes. A separate memory which is holding the data, and the code memory which contains the program code or the instructions. So this is how the process is divided into various sections. And heap memory, as I already told, it is the memory which is used for allocating the dynamic memory to the processes when it is executing. Now process states and the state transition. So the creation of a process till the termination, it is not a single step operation. So from the creation of the process till the process is going to terminate, so the process will change or transit from one state to many state. It will go through many stages of process. There are many stages of the process through which the process will pass through during its lifetime. So that we call it as process life cycle. Now the cycle through which the process changes its state from newly created to the execution completion is known as process life cycle. Now what are those states, or what are the finite states of the process in which the process is going to stay during its lifetime, and how it's going to transit from one state to the another state? So that is what we're going to see in the next slide here. So this is what the process state diagram. Now initially when the process is created, it will be in this state. Now when the process, as long as the process in the disk, we say it is in the created state. Now inserted into the memory, the moment the process is brought into the memory, we say it is in the ready state. That means it is readily waiting for the allocation of CPU for execution. So the moment the CPU is allocated to the process by the scheduler, so it changes the scheduler for execution, changes the state of the CPU from ready to running. Now when the process, I say it is in a running state, it has the CPU and it is executing, currently under execution. When it is executing, lot of things can happen. So one thing is, when it is executing, it may complete its execution, then it goes to the completed state. Now when it is executing, so there may be an interrupt. When an interrupt is generated, so the CPU from the process will be preempted, and the process will be again put to the ready state, and it is again waiting for the allocation of the CPU. And when the process is running, one more thing can happen. What is it? Wait for an IO operation. Now when the process wants to perform an IO operation, it will be moved back to the blocked state or the waiting state. Now here the process wait until the input-output operation is complete. The moment the input-output operation is complete, or the resource for which it was waiting is available, now what it will do, it will again go back and sit inside the ready state, waiting for the allocation of the CPU to have its second chance for running or execution. So this is what the state diagram of the process. So that during the lifetime, the process will change from one state to the another state, and these are all the arrow shows the transition that causes the process to change its state from one to the another. Now these are all the states, created state, ready state, and running state. I have already explained. As I already told, created state is the state when the process is initially created, but not yet loaded into the main memory. So the moment the process is loaded into the main memory, we say it is in the ready list, so ready state, and there is something called as ready queue also. That means the process, once it is in the ready state, it is added to the ready queue, and there it is waiting for the allocation of the CPU. And who allocates the CPU to the process? It is the scheduler. So many different types of scheduling algorithms are there, and that will go for allocating the CPU for the process. Next is the running state. The moment the scheduler allocates the CPU to the process which is there inside the ready state, it gets into the running state, and in the running state it has the CPU and it is performing the execution. And one thing what can happen when it is executing is, it might complete its execution, then it goes to the completed state. When it is there may be an interrupt. When there is an interrupt generated, it goes to again back to the ready state and waits for its turn to get the CPU allocated for one more time. And if it wants to perform an input-output operation or waiting for some kind of a resource, then what will happen is, it goes and sits inside the state called as blocked state, or else you can also call it as the waiting state. So when the meantime, when the input-output operation is complete, or the resource for which the process was waiting is available, it will again get back to the ready state and waits itself for allocating the CPU. So this is what the blocked or the waiting state I told, and the complete state. So because blocked state I have explained, here the process waits until its input-output operation is complete, or the resource for which it was waiting, is available. Now and resources, how it checks, there is something called as semaphores and mutex. This we'll be discussing later. So these are used for providing a synchronized access to the shared resources. Now, so there are many semaphores, again binary semaphores, counting semaphores, and mutex is mutual exclusion. When one process is accessing the shared resource, you should not allow any other process to access the shared resource until the process which is currently using the shared resources releases it voluntarily. So that is what is the blocked or the waiting state. And the complete state, as already told, if the process finishes its execution when it is allocated to CPU, it will move to the completed state. So next is the threads. Thread is again the primitive that can execute the code, and thread is a single flow of sequential flow of control within a process. Now what I can say is that in the normal definition you might be knowing a process is heavyweight and a thread is lightweight. Now why we call process as heavyweight? So we don't call it as heavyweight because it weighs 100 kg, and thread is lightweight because it weighs only 1 kg. So it is not with that context. When we say process is heavyweight, because now when you create multiple processes, every process will get its own copy of the address space. That is address space, as already mentioned. When you create two processes of the same program, because I told the process is an instance of the program, any instances you can create. When you create two processes for the same program, so both the process will be living in their own address spaces. That means, so one more duplicate copy of the code section is given to both the processes, one more duplicate copy of the address data section is given to both the process, stack section is given to both the process, and heap section is given to both the process. So this is what the address space is. Data section, code section, stack section, and heap section, all these sections, they form the address space of the process, and each is given to them. Whenever a new process is created, same one instance of the same program is created, it gets its own separate copy of the address space. Say I have created 1000 instances of the same program. You just imagine how many address spaces will be there. So there will be 1000 address spaces, and every time the CPU switches from one process to the another process, so the address space should also be changed. You got to take out the address space of the old process, and you have to put in the address space of the new process into the memory, and this is a complicated thing. That is the reason we say a process is heavyweight, whereas a thread is known as lightweight, because all the threads are created within the process, and all the threads within the process, they share the same address space, they share the same code, same data they'll share, and of course they have a separate stack. I'll come to that later. So same data memory and code memory they save. That means I can go for creating 100 threads within the process, and all the 100 threads that they will be performing the execution of the different parts of the process, and all of them they live in the same address space. So I can load one address space into the main memory, and I can make the CPU simply switch from one thread to the another thread without having to change the address space. But this was not the case with the process. Now process, when the CPU was to switch from one process to the another process, even you got to change the address space as well. Now here, you can make the CPU easily switch from one process to the another process without having to change the address space, because all the threads of the process live in the same address space. So that is what a thread is known as lightweight process, and process can have many threads of execution, and that is the reason we say, since it is lightweight process, and since when the CPU switches from one thread to the another thread, you need not change the address space. For this reason we say, so thread execution is much faster than compared to the process execution. And here I have shown the small diagram which depicts the same. See, the code memory and data memory is shared by all the processes, but all the threads. So data memory and code memory is shared by all the threads, and each thread has its own stack memory, and they also have their own program counter, because each one of them will be performing the execution of the different parts of the program. Now if I say all of them are sharing the same program counter, then all the threads should be executing the same piece of the code. So that is the reason it has a separate, and why stack memory is separate. Stack memory is given to each thread, because each thread can make a call to the function, and when one thread makes a call to the function, the return address gets saved onto its stack. Now that thread knows how it can go back after the called function is finished. So this is what the thread. Now, concept of multi-threading, so this is what coming. So within a single process, you can have multiple threads. A process is split into multiple threads when which executes a portion of the process. Each thread you can designate to perform the execution of a portion of the process. With this, you can increase the execution time also. You can reduce the execution time and you can increase the response time. Reduce the response time also. So the threaded, this is how it looks, the architecture, thread process diagram. So this is the process, this is the code memory, data memory. This code memory and data memory is common for all the threads. Each one of them have their own stack and then registers. When I say register, there is also a PC present inside this. And this is the main thread which is performing the execution of the main function. This is another thread too which is performing a totally different function. So for example, child thread 1, and this is the thread 2 which is performing the execution of totally different function. Now all of them are living in the same address space. This is one big address space, and this is what. Now the CPU, if it is currently executing this thread, without having to change this address space, it can be made to switch to the another thread. Now what are the advantages of multiple threads to execute a process? So the multiple advantages are there. One is better memory utilization. Why better memory utilization? Because you don't have to load several address spaces into, say I want to perform the execution of I want to make 100 different threads of the same process execute simultaneously, then I don't have to load 100 address spaces into the memory. So what we all need to do is just load one address space into the main memory, the address space of that process into the main memory, and all 100 threads within that process can execute by switching, by sharing the same address space. So and then efficient CPU utilization. Now, why efficient CPU utilization? And this also speeds up the execution. Why speeds up the execution? Because when the CPU switches from one thread to the another thread, so you don't have to change the address space. So you don't have to remove this address space from the memory and put one more address space into the memory. So this need not happen. Hence we say it is execution is faster. And another important thing is efficient CPU utilization. That the CPU is engaged all the time. You have multiple threads within the process, and when one thread wants to perform an input-output operation or wait for some resource or wait for an interrupt, CPU can simply switch to the another thread and perform its execution without having to change the address space. Now thread standards. Now we were saying thread creation. How do we create threads within the process, or the multiple threads within the process? So there are standard libraries which are available in order to do this. So and one common such library is POSIX threads. And this thread, they have the standards also, and the standards are defined by the IEEE. So POSIX thread is normally called as P threads. Now what is this POSIX? POSIX is the Portable Operating System Interface. So and this is the standard for the Unix operating system. So since the invention of the Unix operating system, say the 1970, so from the birth of the Unix operating system till now, there different vendors have created many different versions of the Unix operating system, and ultimately what happened was, it was not possible for the programmers to write the portable application, because the program written on one version of the Unix operating system was not executing on the another version of the Unix operating system. So this because there were many different versions of the Unix operating system, and the API supported by one version of the Unix operating system was not supported by the another version of the Unix operating system. So this was the problem. So writing the portable application was the major difficulty. So later IEEE, what it made, so it made a committee called as POSIX. POSIX is a committee, IEEE, the committee found by the IEEE, and IEEE named that committee as the POSIX, Portable Operating System Interface. And what was the responsibility of this committee, POSIX committee? It was responsible for bringing the standards to the Unix operating system. And this POSIX, they gave standards to the Unix operating system. And again, POSIX, there are many different subcommittees also, like POSIX.1, POSIX.1b, POSIX.1c, and POSIX.4, POSIX.4a, all these things. Now this committee, subcommittee, POSIX.4a, was responsible for giving the standards for the multi-threaded programming. They gave standards for the multi-threaded programming. That means you write your application execution using the multi-threaded programming for one version of the Unix operating system, it also runs on the another version of the Unix operating system, because this POSIX has enforced the multi-programming thread standards across all the versions of the Unix operating system. Now I hope you people understood what is pthread is. Pthread is the library, and why it is called pthread, because it is the POSIX thread, because it functions and this library is written as per the standards of what the POSIX or the POSIX. It is a committee formed by the IEEE just to propose the standard for the multi-threading execution, that is POSIX 4A. And similarly other committees were also there, and each one was responsible for giving standards for other things. Now I have the example here, the POSIX pthread example, one example. This is the API which is used in order to create the thread. So pthread underscore create is this not visible properly because I scanned it. So pthread underscore create is the name of the API which can be used for, so there is a POSIX thread API which can be used for creating a thread, and it takes various arguments. So the first argument is the thread ID. So because every thread, just as I told in the previous session, every process has its own unique process identifier. Thread also has some unique identifier that is called as a thread ID, and this is the attributes, defining the attributes of a thread. You can define the attributes of the thread as well. Many attributes like what should be the stack size, and what should be the how much time the thread can leave, all these things, time to leave. So these are the attributes, and this is the next argument, start function. This is the name of the function which you are assigning for the thread to execute, because I told thread can be made to execute different parts of the process. Now when you're creating some thread, you define which function it should go for executing. And last one is the list of arguments which are passing to this function. So that I have already explained here. It's a new thread, ID of the newly created thread. So this is the data type for holding the thread attributes, and then start function. This is the function which you're assigning for the thread to execute, and arguments is the list of arguments that are passed to this particular function that is assigned to the thread. Now we have another POSIX API, that is pthread underscore join. Now when the main thread creates the thread in order to perform the execution of different parts of the process, the main thread it just blocks the current thread or the main thread and waits until the completion of the thread pointed by it. So the main thread creates one more thread, and this main thread blocks itself, waiting for the other thread to complete its execution. So the moment you make the main thread create some threads, and you got to make the main thread keep itself blocked, waiting for the other thread to go ahead